Hi, Chem 110. In a previous video, we looked at esters and briefly introduced them. We looked at how esters can be formed through a reaction called esterification, where we joined a carboxylic acid with an alcohol. And now we're going to be naming esters. And so naming esters really boils down to breaking it apart back into the carboxylic acid and the alcohol and looking at what those original names would have been. And so if we look here at the molecule drawn here, which is actually the flavor and smell of pineapples, this is ethyl butanoate. And so we're going to break this down into what used to be an what used to be an alcohol, and then what used to be the carboxylic acid. So this would have been an ethanol, and over here would have been a 4-carbon carboxylic acid. So it would have been butanoic acid. But if we give it the ion name, it would have been butanoate. So we're going to name this overall the alcohol's name first, but we're just going to drop the all and give it just an ethyl. Ethyl butanoate. So it's as if we have this carboxylic acid ion attached to an ethyl group. I guess you can look at it that way. So here we've got a 2-carbon carboxylic acid with 1 carbon attached. So this is ethanoic acid, or would have been ethanoic acid. The ion is, of course, ethanoate. And over here is a methyl, so we're going to name it methyl ethanoate. Other examples here. Here's an ethyl and an ethyl. So ethyl ethanoate. Here we've got a methyl attached to a 3-carbon carboxylic acid ion, so methyl propanoate. This one's a little bit tricky looking, but it's not bad. We've got an ethyl, so 2 carbons, and the carboxylic acid portion was attached to a benzene, so ethyl benzoate. So just by breaking these down into each side of that ester, we can name them appropriately. Okay, let's talk about some of the properties of esters. Of course, we've already hinted towards the fragrance and perfumes that esters play a role in terms of fruit and flowers. And the reason why we can smell them so easily is because they are volatile. So that means that it's really quite easy for them to kind of get up and leave in the atmosphere, into the air. Otherwise, of course, they would not get into our olfactory sensors in our nose. They are soluble in water, and so we will be able to taste them. So in this image here, we see grapes, and the odor of grapes is due to the ester called ethyl heptanoate. So we would have a 7-carbon long, originally carboxylic acid. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And this is why line angle structure is, of course, much better. And then an ethyl, just two carbons. So that is the chemical structure for ethyl heptanoate, the scent of grapes, the scent and actual taste of grapes. So other examples, pears, propyl ethanoate, bananas, pentyl ethanoate. Oranges is octyl ethanoate, pineapples, ethyl butanoate, and apricots, you can see is pentyl butanoate. And hopefully in lab, our plan is to be making some of these fragrant esters in the upcoming weeks. Another lab activity that we will hopefully be partaking in is linking to health. And we did allude to this in a previous lecture, but I want to go over it quickly again. So here we have got an image of methyl salicylate, and this is kind of a different naming system, so don't worry about the name of this right now. But this is wintergreen oil. And so we can actually distill this out of wintergreen leaves. And if you look closely here, we have an ester functional group. And so oil of wintergreen, of course, methyl salicylate. Don't worry again about that naming. It's okay. This is kind of a large chemical, and that is not its IUPAC name, of course. It's a very pungent, very minty odor. It can be used in salves for skin ointments. It can pass through the skin, and so in that way it can be used as a pain reliever. It actually also acts as a counter irritant, so like to soothe sore muscles. And in fact, if we were to effectively take off this methyl group, we would have an item called salicylic acid. So we're kind of going in reverse here, salicylic acid. Of course, if we join salicylic acid with a methyl alcohol, so a methanol, then we would get our methyl salicylate. But working backwards, we can take this back off and form the salicylic acid. Now, the reason why I want to work backwards is because if we have salicylic acid here, which of course, if we take this methyl group off, and reform the carboxylic acid. So go from this ester to a carboxylic acid, which is salicylic acid. We can turn it then and rejoin it with a different item. So in this case, we'll be taking this alcohol and this carboxylic acid and making an ester somewhere else. And this is aspirin. And so in lab, hopefully we will be able to do this. Hopefully we'll be able to set up a lab where we can take wintergreen leaves, here we go, wintergreen leaves, and distill out oil, turn it into salicylic acid, add acetic acid, which is essentially just vinegar, and that will bond onto this alcohol group, forming an ester here. So what's interesting is depending on what I join the salicylic acid with, I can make an ester in a couple of different places. If I join it with an alcohol, I can make an ester here. If I join it with a different carboxylic acid, I can join an ester here, like we did here. So we have a couple of different options here. So we can make aspirin, shown here, or we could start with salicylic acid, join methanol, and make wintergreen oil. So pretty cool little chemical. Okay, let's talk about the properties of esters in terms of boiling points and solubility in water. So, we have alluded to the fact that we can smell these and taste these, so they must be soluble in water and must be somewhat volatile. And so the boiling points of esters are typically higher than those of alkanes and ethers, but usually lower than those of alcohols and carboxylic acids of similar masses. And that is because they have this carbonyl in them, which could potentially have dipole-dipole potential interactions, but they don't have the capability of forming any type of hydrogen bonding with themselves. Now, in water, of course, here is our ester molecule. Here we have this dipole, slightly polar double bond between carbon and oxygen. It can use the hydrogens of the water molecules to form to form hydrogen bonds. So the partially negative oxygen could potentially hydrogen bond with the partially positive hydrogen of the water molecules. But of course, this will only go through to esters that have about 5 or fewer carbons in them, because of course then at that point we'll start getting a lot of hydrophobic interactions because of those carbons. Hydrogens are hydrophobic. Okay, so we have the idea that we can form an ester by joining a carboxylic acid and an alcohol. But we can also take an ester and break it back down. And we saw that briefly a moment ago when we were talking about wintergreen oil breaking apart back down into salicylic acid and methanol, when we were working backwards in that chemical reaction a few slides ago. And so we have what's called the hydrolysis of esters then. And we can have it in 2 different forms. We could have an acid hydrolysis or a base hydrolysis. And we are going to start with the acid hydrolysis here. And that just denotes the fact that the catalyst is an acid. So an ester reacts with water to produce carboxylic acid and an alcohol. So our components here, the carboxylic acid and the alcohol, are going to break back apart into kind of what we would have thought of their original components. So if we would have had an ethanoic acid, so a 2-carbon carboxylic acid, then that's what we're going to get here. And then a methanol, that's where we're going to get here. And we'll see that the ester's oxygen will go with the alcohol. So that in blue is here. And that the water that will be in our solution is going to donate an OH, so an oxygen and a hydrogen, to be the OH part of our carboxylic acid. So we see that in red. Okay, so let's go to the whiteboard. Okay, so let's see what this is going to look like. So we'll take a pretty simple ester. We'll take, oops. Okay, and so we've got acid catalyst. So I'm just going to use a hydronium ion. You could use hydrochloric. It really doesn't matter. Anything that's going to donate NH plus really will work. And so what we'll see is that our carbonyl oxygen is going to attack a hydrogen from our acid. And the electrons that held this on to the acid are going to go back onto the leftovers of the acid. So in this case, this is just going to form water. And then we will have an intermediate that looks like this. Okay, so we've still got the carbonyl double bond. But now we've got a hydrogen brought on. And of course, that gives us oxygen 3 bonds and only 1 free pair of electrons. So it's got a plus charge, and that is not stable. Luckily, we've got a water. We are in aqueous solution. Perhaps this is even the water that we've just formed. And it is going to attack onto the carbon of the carbonyl. And the electrons that are part of this double bond are going to go onto the oxygen and sequester that plus charge. And so we will have a intermediate next that looks like this. Okay, so here's my central carbon. The original oxygen, carbon, hydrogens, free electron pairs. We've brought in a water molecule which has 1 pair of electrons, 3 bonds, plus charge, unstable, unhappy. And now we are attached to a single bond oxygen up above, 2 free electron pairs, hydrogen from the acid. So I've just kind of shifted that oxygen carbon kind of down to make room, and that's okay. All right. So here we've got another water. And it's going to essentially attack our acid originally, our acid hydrogen, and those electrons are going to fold back down and recreate a double bond. And what we'll see is that that's going to essentially force the carbon-oxygen atoms, the carbon-oxygen electrons here to deposit onto that oxygen. And as it does so, we're going to have a hydrogen rearrangement where one of our hydrogens from this unstable water is going to come on over. So just a hydrogen rearrangement, a transfer of a proton, then converts this into a good leaving group. So we're really just transferring a hydrogen from this spot to this spot. And we will kick off CH3O H. So there is our alcohol. Now up above, we have reformed our original hydronium, our original acid. By taking that hydrogen back off the top. And that has collapsed down right here back into a double bond. So we're left here with this double bond oxygen. The alcohol came from my first water molecule in blue. And then when I say alcohol, I mean the OH part of the carboxylic acid. And then methanol had been kicked off. So I've got a carboxylic acid. I've got ethanoic acid and methanol as my products. And so this was the acid catalyzed ester hydrolysis. And I'm specifying acid catalyzed because, of course, next we'll do a base catalyzed. Let's go back to our PowerPoint quickly. So we had actually a couple of water molecules. We had acid heat in there, and we broke apart our carboxylic acid from our alcohol. So here in this step, for example, if we had aspirin, we could undergo hydrolysis at this location. Let me actually move this over. At this location. and turn this into salicylic acid and acetic acid. Okay, so I mentioned that we did the acid hydrolysis. We also have base hydrolysis. The end results are not quite the same. And so in a base hydrolysis, first of all, it's called saponification. And this is actually involved in soap making. And we will be hopefully doing this in lab too. And when I say hopefully, it really just depends on how well we do in terms of spacing out our labs and how long we have and how many of them we can do. So hopefully we'll be able to make soap through saponification. And so in this case, we'll start with an acid, and we'll start with an ester, and we add a strong base, so something like sodium hydroxide, and heat. And when we break this apart, it's a different mechanism. And instead of just forming the carboxylic acid and the alcohol, we're still going to form the alcohol, but now we don't have the acid formed. What we have is the acid's salt. So we're making a carboxylate salt and the alcohol. And so this is actually in the process of making soap. And when I say soap, I actually mean soap, like washing your hands. And so let's go to the whiteboard and see what this looks like. Okay, so we'll again start with a really simple ester. Okay, and then again, in this case, we're starting with a base. And if you remember, if we were to put something like, I'm going to kind of go off to the bottom here. If we were to put something like NaOH into an aqueous solution, so if we were to dissolve this into water, we would get Na ions and we would get OH ions. So we would, of course, get this dissociated. So we would have salt ions and we would have hydroxide ions. And so I'm just going to really need the hydroxide ions for this particular catalyst. But of course, when we form the salt, we will be looking at the sodium to pair with it. So here is this free hydroxide in solution. And it is going to attack the partially positive dipole portion of our carbonyl, so that carbon. And that is going to force the electrons of one part of this double bond up onto the oxygen there. It will then form an intermediate that looks like this. Single bond. So now 3 free electron pairs here. This carbon has brought in another OH, so that's bound on. And let's go ahead and make this incoming OH black. And it is still hanging on to the OCH3 that it originally had. Okay, so my original carbonyl has now only got a single bond, but that oxygen has those 2 electrons deposited on top of it and has now a negative charge. And what's going to happen next is one of those free electron pairs is going to come on down, redeposit to reform a double bond, and that's going to force carbon to let loose one of its bonds. And the most stable one to let loose is going to be the one that that's keeping it on with the essentially an ether. So this OCH3. So the electrons that are holding this in place are going to deposit onto that oxygen, and we're going to kick off an O, which has gained the electrons from its bond with carbon, CH3. So that has come off. And what we're left with up above at this point is an intermediate that looks like this. Now we've redouble bonded. OH has come on in. This isn't really cool. Not really going to hang out like that because this what should be methanol. So I'm going to put in parentheses, it should be methanol, is not stable with this negative charge. And in fact, if the carboxylic acid above had a negative charge, it would be more stable. So what's going to happen is my methanol is actually going to steal the hydrogen off of this end. So it actually is going to turn itself into methanol. So we're going to get another step that looks like this. So we've lost that hydrogen. We have a negative charge, but methanol now has brought that hydrogen to itself. And it is complete. And we now have an ethanoate ion which is essentially done and will pair with a free sodium ion in solution. Now, if we let this go long enough, it is possible that I can work with water in solution and take on a hydrogen and completely become the carboxylic acid, the ethanoic acid. And that's possible too. But for our purposes and for what we're seeing in your book, we're going to stop at the carboxylate ion that's shown here. And we've got ethanoate ion, which I have spelt wrong. Sorry, ethanoate ion, which will pair with the original sodium if we had used sodium hydroxide as the strong base catalyst. And we've got methanol. And so this was the base catalyzed ester hydrolysis. And so the acid and the base catalyzed ester hydrolysis do not necessarily yield the same results, because here we can see that it's potential to get the carboxylate ion. Again, if we leave this in solution long enough, it is possible for this carboxylate ion, in this case ethanoate ion, to work with water to fill in that negative charge to bring on a hydrogen to become the full carboxylic acid. That is possible. Okay, so with that, it actually brings us to the end of the chapter. We're going to hopefully be coming back to these reactions throughout the next couple of weeks, meaning that even though we're going to be moving forward with the material out of the book and out of Moodle, we're going to be revisiting these items in lab. So please, revisit these videos as often as you need and ask questions as you need.